We define the term impedance as this combination of the resistance, inductive reactance, and capacitive reactance. It has a unit of ohms. It's essentially the AC version of resistance, if you want to think of resistance as a DC term. So impedance, important term to remember. Along with that, we talked about the phase angle. This tells us whether the current will ultimately lag or lead the voltage in the circuit. And this is what we call phi, and that's the arctan, as we said before, of the x sub L minus x sub C over R. Depending on the sign, if the angle is positive, we call the circuit inductive because the inductance is stronger than the capacitance. If the angle is negative, we call this a capacitive circuit because the capacitive reactance is stronger than the inductive reactance. And in fact, this is exactly what this slide is showing you. X sub L greater than x sub C, high frequencies, in other words, current will lag applied voltage. We call the circuit an inductive circuit. If phi is negative, it's a capacitive circuit. The current will ultimately lead the voltage. And of course, if phi is 0, that means that the two reactances are the same, and the circuit is purely resistive. It's only the resistance that matters in that case. Well, along with this, we want to talk about the power in an AC circuit. We can talk about this, the average power being converted to internal energy and the resistance in this way. We talk about the average power as 1/2 I max times V max times cosine phi. We call the cosine phi the power factor of the circuit. We can also find the average power in terms of the resistance because resistance is where it's being dissipated. It's I squared RMS times the value of the resistance. And of course, in the case where I have only a resistive circuit, the average power is very simply the IRMS times the VRMS values, as you might expect. So in this case, we expect power being converted to internal energy in a resistor. We said that before. But what that also means is you don't expect to have power losses in capacitors and inductors in an AC circuit. What is happening in the capacitors during the first half of the cycle, we store energy, and during the other half of the cycle, the energy is returned to the circuit, and the capacitor loses, is not the cause of any power losses. Same thing for the inductor. In an inductor, the source does the work against the back EMF, and then energy stored in the inductor. But then the circuit begins to decrease the current begins to decrease in the circuit, and the energy is returned to the circuit. So the power delivered by the AC circuit will depend on the phase. We can also talk about resonance in an AC circuit. We talk about a resonance frequency omega naught where the current has its maximum value. And that's going to occur when the capacitive reactance is equal to the inductive reactance. That frequency then would be equal to 1 over the square root of LC. And of course, as you might remember, LC corresponds, 1 over square root of LC corresponds to the natural frequency of oscillation of the LC circuit. We studied that in the last chapter. So RMS current has a maximum value when the frequency of the applied voltage is equal to that natural oscillator frequency. We say that we have a resonance. And we can see that in the following case. Let me go back to it. We can look for resonances here. As the resistance decreases, the curve becomes narrower and taller for AC circuits until, of course, we can get the resistance down to essentially 0. We have almost a delta function at the resonant frequency. we can express this as the power as a function of frequency in the following way. A more complicated expression with our VRMS in the numerator, and then you see this complicated expression in the denominator. And of course, if you want to maximize the power, you notice that at resonance, your average power will be at a maximum. So that's something to remember about resonance in a circuit. Associated with that, we talk about a quality factor. Quality factor is a dimensionless factor that we let equal Q, not to be confused with charge, by the way. In this case, it's equal to the resonant frequency divided by a delta frequency, which is a width of a curve measured between two values of omega, for which the power has half of its maximum value, or half power points. If I have a high Q circuit, I have only a narrow range of frequencies. A low Q circuit detects a much broader range of frequencies. So one good example of how that works is with a radio receiving circuit, because that would be a really good example of where you want to have a resonance. You want to create a resonance at the frequency at which a station is broadcasting, so your receiver can receive that signal strongly and then transmit it to sound, or transduce it to sound. I'm going to change gears a little bit. Another really great example of AC circuits is the transformer. This is a device that can take, for example, let's talk about the high voltages that come from your power lines outside your house, and step it down to 110 volts so that you can use them for your appliances in your normal outlets in your house. So that's an example of a nice use for a transformer. It's essentially a soft iron square where we wrap two coils around the wire, around the iron. We have an AC source at one side, and we have an output at the other. Depending upon the ratio of turns of the wire, N1 or N2, that will tell you if the transformer is a step-up transformer where the voltage coming out is larger than what's going in, or a step-down transformer where the voltage is less coming out than going in, as the example I used for your getting the energy for your house from the power lines. What the soft iron core, the purpose of that is just to increase the magnetic flux and increase the signal. If we use a laminated core, we minimize losses due to eddy currents. Typically, we have very high ratios for efficiency for transformers, 90 to 99%. And so in the primary, we talk about the voltage that's induced, number of turns times the change in flux with time. In the secondary, the voltage across the secondary would be the number of turns in the secondary, again, times that same flux factor. Therefore, that's why we say that in the case of a step up and step down transformer, if the number of turns in the secondary is larger than the number of turns in the primary, we have a step up transformer. That means you're going to have more voltage coming out than going in. And the reverse is the case if the number of turns in the secondary is less than the number of turns in the primary. Ultimately, the power output in the primary equals the power output of the secondary, and so we see this ratio applies very well. Transformers may be used to match resistances between primary circuit and the load. That way we can ensure a maximum power transfer. In this case, the stereo applications are finding, like between your amplifier and your speakers, a way of impedance matching, causing impedance matching between your stereo amplifier and your stereo speakers. That's a nice application of that. We also have rectifiers. A way of converting an AC current to a DC current is called rectification. Any device that does that is called a rectifier. Probably the most common rectifier is called a diode. A diode's a circuit element that conducts current in one direction, but it blocks current from the other direction. And it will look something like this. If I have a rectifier circuit, what it will do is it will eliminate the negative currents, and I will only have positive ones, like so. If I use a capacitor to filter the signal, I can get an almost steady signal rather than an oscillating one. So if I add a capacitor to my diode circuit, that will serve that purpose. Oftentimes we put capacitors onto power supplies to regulate the signal to make it much more steady if it happens to be too variable for our purposes. The capacitor in this case is what we call a half-wave rectifier because it's rectifying the current during only half of the cycle. That's one example of a rectifying device. We also have filter circuits. So in the case of a filter circuit, we're trying to smooth out time-varying signals. Even after a signal is rectified, you might have a small AC component that we call a ripple. But if I can filter the circuit, I can reduce the ripple as much as possible. There are two types of filters we can talk about. Actually, there are more than two, but we'll talk about two today. The high-pass filter, you see, is a filter with a capacitor and a resistor. This is one that will only pass higher frequencies rather than lower frequencies. And you see we have the capacitor here and the resistor here. On the other hand, we can have a low-pass filter where we exchange the two elements. And so what we have is the case where only low frequencies are passed as opposed to high frequencies. When you talk about crossovers in speakers, crossovers in speakers use high-pass and low-pass filters, or sometimes band-pass filters where they're filtering out both highs and lows, depending on what type of frequencies you want to hear. So if you're using a woofer, you want to use a low-pass filter so that the low frequencies come to that particular speaker or component of your speaker. Using the tweeter, then you want to use a high-pass filter so only the high-pass frequencies come to the tweeter and are transmitted through that part of the speaker. So this is a very quick exposure to AC circuits. I hope that this will be informative and will enable you to perhaps study further in AC circuits for those who have the interest. And next time we're going to take a small diversion into waves and then electromagnetic waves. So we will see you next time.